When we think of a volcano, a very specific image often comes to mind. We picture a towering, conical mountain, its peak wreathed in smoke and ash. We imagine fiery fountains of molten rock erupting into the sky, painting the heavens with shades of orange and red against a dark, dramatic backdrop. It is a spectacle of raw terrestrial power, a reminder of the Earth's restless energy simmering just beneath our feet. These land-based volcanoes, from Mount Vesuvius to Mount Fuji, have shaped human history, culture, and mythology for millennia. They are the titans of our landscapes, their eruptions powerful enough to bury cities and alter the course of civilizations. This is the image we know, the story we tell ourselves about the planet's geological heart. Yet, this familiar picture represents only a tiny fraction of the whole truth. It is a mere glimpse into the volcanic activity that constantly reshapes our world. The vast majority of Earth's volcanoes do not stand proudly on continents, visible to all. Instead, they lie hidden from our view, concealed beneath the immense crushing weight of the world's oceans. These are the submarine volcanoes, the silent giants that operate in the perpetual darkness of the deep sea. They are the planet's secret majority, a network of volcanic systems far more extensive and active than anything we can observe on land. Their existence challenges our land-centric perspective and invites us to consider a world of geological forces that operates on a scale difficult to comprehend. Imagine a world where the longest mountain range is not the Andes or the Himalayas, but a colossal chain that winds its way around the entire globe, completely submerged. This is the Mid-Ocean Ridge System, a 65,000-kilometer-long series of underwater volcanoes that is constantly birthing new oceanic crust. It is here, in the cold, high-pressure environment of the abyss, that most of Earth's volcanic activity unfolds. These eruptions are not the explosive displays we see on land. They are quieter, more effusive events, yet their cumulative impact is staggering. They are the tireless engines of plate tectonics, driving the continents apart and paving the ocean floors with fresh rock, a process that has continued unabated for eons. This hidden realm of fire beneath the water is not just a geological curiosity, it is a fundamental force that has shaped our planet in profound ways. These underwater volcanoes build islands from the seafloor up, creating new lands that eventually break the surface of the waves. They trigger devastating tsunamis that can travel across entire ocean basins, threatening coastal communities thousands of kilometers away. They pump heat and chemicals into the ocean, influencing currents and nurturing bizarre ecosystems that thrive without sunlight. Today, we embark on a journey to this mysterious world to discover how these hidden volcanoes influence everything from the air we breathe to the very origins of life on Earth. The sheer scale of submarine volcanism is almost beyond human intuition. While a single terrestrial eruption can capture the world's attention for weeks, the activity beneath the waves is ceaseless and widespread. It is estimated that more than 80% of all volcanic eruptions on Earth happen underwater. These are not isolated events, but part of a continuous global process. Day after day, year after year, immense quantities of magma well up from the mantle to meet the cold seawater of the deep. This is the fundamental mechanism of seafloor spreading, the process that creates the very ground beneath the oceans. The seafloor we sail across is, in geological terms, remarkably young, constantly being renewed by this hidden volcanic engine. This constant creation of new crust makes submarine volcanoes the primary architects of our planet's surface. The Mid-Ocean Ridge System is the epicenter of this activity, a global seam where tectonic plates are pulled apart. Here, magma rises to fill the gap, solidifying into new rock. Unlike the dramatic ash-laden eruptions on land, deep-sea eruptions are often subdued affairs. The immense pressure exerted by kilometers of overlying water suppresses the explosive release of volcanic gases. This pressure prevents the magma from fragmenting into ash and instead encourages it to ooze out onto the seafloor, forming distinctive bulbous shapes known as pillow lavas. These formations are the telltale sign of lava cooling rapidly in an underwater environment. The term pillow lava perfectly describes the appearance of these unique volcanic rocks. As molten lava emerges from a vent on the seafloor, its outer surface is instantly chilled by the near-freezing water, forming a solid, glassy crust. However, the interior of the flow remains molten and continues to push forward, causing the pliable crust to stretch and expand like a balloon. Eventually, the pressure becomes too great and the crust cracks, allowing a new lobe or pillow to bud off and repeat the process. Over time, these interconnected lobes build up, creating vast fields of pillow basalts that cover millions of square kilometers of the ocean floor, a silent testament to the relentless volcanic activity hidden in the deep. While these eruptions may lack the explosive drama of their terrestrial counterparts, their collective output is monumental. It is estimated that underwater volcanoes produce around 3 cubic kilometers of lava each year. This is enough molten rock to resurface the entire ocean floor over geological time, burying older crust as it moves away from the mid-ocean ridges. This process is not just about creating new ground, it is a critical part of the Earth's life cycle. It drives the movement of continents, recycles elements between the mantle and the crust, and ultimately dictates the shape and chemistry of the oceans themselves. These silent architects work tirelessly in the dark, building the world we know from the bottom up. The deep ocean is a realm of extremes defined by crushing pressure, absolute darkness, and freezing temperatures. These conditions profoundly influence the behavior of underwater volcanoes, often taming what would otherwise be violent eruptions. At depths of several kilometers, the weight of the water column is so immense that it acts like a lid on a pressure cooker. It prevents the volcanic gases dissolved within the magma, such as water vapor and carbon dioxide, from expanding rapidly. As a result, many deep-sea eruptions are gentle, effusive flows rather than explosive blasts. Magma simply seeps out onto the seafloor, building up layers of pillow lava or smooth sheet-like flows over vast areas, a quiet and constructive process that goes largely unnoticed at the surface. However, this picture of serene, deep-sea volcanism is not the full story. The character of an underwater eruption changes dramatically with depth. As a volcano grows taller, or if it is located in shallower waters near coastlines or on submarine plateaus, the confining pressure of the overlying water decreases significantly. With less weight to hold them in, the dissolved gases within the magma can escape with explosive force. When superheated magma at temperatures exceeding 1000 degrees Celsius comes into direct contact with seawater at these shallower depths, the result is a violent interaction. The water flashes instantly to steam, expanding to over 1,700 times its original volume in a fraction of a second, triggering a powerful phreatomagmatic explosion. The world witnessed the terrifying power of such an event in January 2022, with the eruption of the Tonga Ha'apai volcano. This submarine volcano, with its caldera lying just 150 meters below sea level, produced one of the most violent explosions ever recorded in the modern era. The blast was heard as far away as Alaska and sent atmospheric shock waves circling the globe multiple times. It generated a plume of ash, gas, and water vapor that rocketed an unprecedented 58 kilometers into the atmosphere, breaching the mesosphere. The eruption displaced a colossal volume of water, triggering tsunamis that caused devastation in the nearby islands of Tonga and were detected across the entire Pacific Ocean, from Japan to the shores of Peru. The Tonga Ha'apai event served as a stark and powerful reminder that submarine volcanoes are not always silent or gentle. They are capable of unleashing incredible destructive energy with consequences that can be felt on a global scale. This single eruption injected a massive amount of water vapor, a potent greenhouse gas, into the stratosphere, an event that scientists are still studying for its potential short-term effects on global climate. It demonstrated that the transition from a deep, high-pressure environment to a shallow one can turn a gentle giant into a cataclysmic force, posing a significant and often unpredictable hazard to our interconnected world. These volcanoes are a potent link between the deep ocean and the high atmosphere. Despite their immense importance in shaping our planet, the world of underwater volcanoes remains one of the last great frontiers of exploration on Earth. We currently have more detailed maps of the surface of Mars and the Moon than we do of our own planet's seafloor. The vast majority of the ocean floor lies uncharted and unexplored, a mysterious realm hidden beneath kilometers of water. It is estimated that there are over 1 million submarine volcanoes, or seamounts, scattered across the ocean basins, yet only a tiny fraction of these have ever been visited, mapped or studied in any detail. Each one represents a potential source of geological activity, a unique habitat for marine life, and a piece of the puzzle of how our planet works. Exploring this hidden world presents formidable challenges. The deep ocean is an environment hostile to both humans and technology. The crushing pressure can implode all but the most robustly engineered vehicles. The corrosive saltwater relentlessly attacks equipment, and the complete absence of light makes navigation and observation incredibly difficult. For centuries, our knowledge was limited to what we could infer from volcanic islands that breached the surface, or from rocks dredged blindly from the depths. This meant that our understanding of submarine volcanism was fragmented and incomplete, based on indirect evidence rather than direct observation of these incredible geological systems in action. The last few decades, however, have ushered in a golden age of deep-sea exploration. The development of advanced technologies is finally allowing us to pull back the curtain on this mysterious domain. Sophisticated sonar systems mounted on research vessels can now create high-resolution maps of the seafloors, revealing the intricate topography of mid-ocean ridges and the precise locations of thousands of previously unknown seamounts. Remotely operated vehicles and autonomous underwater vehicles, unmanned robotic submarines can dive to the deepest parts of the ocean. Equipped with powerful lights, high-definition cameras and robotic arms for collecting samples, these vehicles act as our eyes, ears and hands in the abyss. This technological revolution is transforming our understanding of the planet. We can now witness underwater eruptions in real time, study the bizarre creatures that thrive around hydrothermal vents, and analyze the chemical soup that these volcanoes release into the ocean. Each new dive brings new discoveries, challenging old theories and opening up new avenues of research. This journey into the abyss is more than just an adventure, it is a critical scientific endeavor. Understanding these hidden volcanoes is essential for assessing natural hazards like tsunamis, for discovering new biological and mineral resources, and for comprehending their profound influence on ocean chemistry and global climate. The secrets they hold could quite literally change everything. When we imagine the great mountain ranges of our world, our minds turn to the towering peaks of the Himalayas, the rugged spine of the Andes, or the ancient Appalachians. These are the titans of our continents, landforms that have shaped human history, dictated weather patterns, and inspired awe for millennia. They are colossal, visible reminders of the immense geological forces that sculpt our planet's surface. Yet the largest and most extensive mountain chain on Earth is not found on any continent. It lies hidden from sight, submerged beneath the vast dark waters of the world's oceans. This is the mid-ocean ridge system, a continuous chain of underwater volcanoes that stretches for an astonishing 65,000 kilometers around the globe like a seam on a baseball. This submerged mountain range is a truly global feature. It winds its way through every major ocean basin, a colossal scar on the planet's crust. It runs down the center of the Atlantic, curves around Africa, crosses the Indian Ocean, and sweeps across the vast expanse of the Pacific. In most places, its peaks lie 2 to 3 kilometers below the ocean surface, shrouded in perpetual darkness. Only in a few locations, such as Iceland, does the ridge breach the waves, offering us a rare glimpse of the volcanic processes that are constantly at work along its entire length. This is not a static, ancient mountain range. It is a dynamic, living system, the most volcanically active feature on our planet. The sheer scale of the mid-ocean ridge is difficult to comprehend. If you could drain the oceans, it would be the most dominant feature on Earth, dwarfing anything we see on land. It forms a network of rift valleys, jagged peaks, and immense fracture zones that crisscross the seafloor. Its total length is nearly 10 times that of the Andes, the longest continental mountain range. This is the true backbone of our planet, the place where the Earth's crust is born. It is the heart of the plate tectonic system, a vast volcanic engine that has been running for hundreds of millions of years, tirelessly shaping and reshaping the world we know. Understanding this hidden mountain range is fundamental to understanding how our planet functions. It is not merely a collection of underwater mountains. It is the primary site of crustal creation. Along its entire length, magma from the Earth's mantle rises to the surface, cools and solidifies to form new oceanic crust. This process is happening right now as you read this. Deep beneath the waves, the Earth is expanding, pushing continents apart and paving the ocean floors with fresh, volcanic rock. The secret majority of Earth's volcanoes reside here, working silently in the deep to build the very foundation of our oceans. The mid-ocean ridge is far more than just a geological feature. It is the engine room of plate tectonics. This is the theory that describes how the Earth's outer shell is broken into large, rigid plates that move and jostle against one another. The ridges are the divergent plate boundaries, the places where these colossal plates are being pulled apart. Think of it as a giant slow-motion conveyor belt. As the tectonic plates on either side of the ridge move away from each other, a gap is created. This reduces the pressure on the hot, pliable mantle rock beneath, allowing it to melt and form magma. This molten rock is buoyant and rises to fill the void, erupting onto the sea floor. This process, known as seafloor spreading, is the fundamental mechanism driving the movement of continents. The Atlantic Ocean, for example, is widening by a few centimeters every year, about the same rate your fingernails grow as the North American and Eurasian plates move apart. This is driven by the constant volcanic activity along the mid-Atlantic ridge. The new crust formed at the ridge is hot and elevated, creating the mountainous topography of the ridge itself. As this new crust moves away from the ridge over millions of years, it cools, becomes denser and sinks lower, forming the deep abyssal plains that cover much of the ocean floor. This continuous creation of new crust means that the ocean floor is geologically very young. While the continents contain rocks that are billions of years old, the oldest oceanic crust is only about 200 million years old. The seafloor is in a constant state of renewal. The rock beneath your feet on land might have witnessed the dinosaurs, but the floor of the Pacific Ocean is being repaved as we speak. The old oceanic crust is eventually recycled back into the mantle at subduction zones, where one plate dives beneath another. This elegant cycle of creation at mid-ocean ridges and destruction at subduction zones is the engine that drives almost all of Earth's geological activity, from earthquakes to the formation of continental mountain ranges. Therefore, the silent eruptions along the mid-ocean ridge are not isolated events. They are the heartbeat of a living planet. Every flow of lava, every plume of heated water is a part of this grand global process. It is a system that recycles the planet's elements, regulates the transfer of heat from the Earth's interior, and ultimately dictates the geography of our world. Without the constant hidden volcanism of the mid-ocean ridges, the continents would be static, the oceans would not have their present form, and the Earth as we know it would simply not exist. This is the powerful hidden force that shapes everything. While a land volcano might erupt spectacularly for a few weeks or months, and then fall silent for centuries, the volcanic activity along the mid-ocean ridge is a continuous, unending process. It is less like a single dramatic explosion and more like a wound on the Earth's surface that never stops bleeding magma. Along the 65,000-kilometer length of the ridge system, eruptions are happening somewhere at almost all times. We may not see them and we may not feel them, but they are a constant feature of our planet's geology. This makes the mid-ocean ridges collectively the most volcanically productive structures on Earth, responsible for creating more new rock than all other volcanoes combined. The style of this eruption is dictated by the unique environment of the deep ocean. At depths of several thousand meters, the pressure is immense, hundreds of times greater than at the surface. This incredible pressure, exerted by the colossal weight of the water column above, has a profound effect on the behavior of the erupting magma. It suppresses the violent expansion of volcanic gases like carbon dioxide and water vapor, which are the primary drivers of explosive eruptions on land. Instead of blasting ash and rock high into the air, the magma tends to ooze and flow out of fissures in the seafloor in a much calmer, more effusive manner. Imagine a crack in the Earth's crust, miles below the ocean's surface. From this fissure, molten rock at over 1,000 degrees Celsius emerges into the near-freezing seawater. The eruption is not a fiery fountain, but a steady outpouring of lava that spreads across the ocean floor. These are known as fissure eruptions, and they are the hallmark of the mid-ocean ridge. The lava flows can form vast smooth plains known as sheet flows if the eruption rate is high, or they can create the lumpy bulbous structures known as pillow lavas if the flow is slower. This process builds up the volcanic crust layer by layer over millions of years. The total volume of magma produced by these unseen eruptions is staggering. Scientists estimate that the mid-ocean ridge system generates around 3 cubic kilometers of new crust every single year. To put that into perspective, it is enough lava to cover the entire city of London with a layer of rock nearly 2 meters thick. Year after year, this process continues, pushing the tectonic plates apart and resurfacing the ocean basins. It is a slow, methodical and relentless construction project on a planetary scale, all happening in the silent, dark depths of the sea. One of the most characteristic features of the volcanic landscape at mid-ocean ridges is the widespread presence of pillow lavas. These remarkable formations are the definitive signature of lava erupting and cooling in an underwater environment. They look exactly as their name suggests, vast jumbled piles of rounded pillow-shaped rocks, often stacked on top of one another. They cover millions of square kilometers of the ocean floor, a testament to the countless eruptions that have occurred along the ridges for eons. The formation of these pillows is a beautiful and fascinating process, a direct result of the dramatic interaction between scorching hot magma and icy cold seawater. The process begins when magma emerges from a vent on the seafloor. As the molten rock, at temperatures of up to 1,200 degrees Celsius, makes contact with the water, which is often only a few degrees above freezing. Its outer surface is instantly quenched. This rapid cooling forms a solid glassy crust or skin around the still molten interior of the flow. This skin is flexible like a balloon. As more lava pushes from behind, it inflates this pliable crust, causing it to swell outwards into a bulbous lobe-like shape. This entire process happens in mere seconds, freezing the shape of the flow in place. As the pressure inside the newly formed pillow continues to build, the outer crust eventually cracks under the strain. A new jet of molten lava then bursts through the crack, and the process begins anew, forming another interconnected lobe. This budding process can repeat over and over again, with new pillows emerging from the sides or fronts of older ones. The result is a complex, interconnected chain of tube-like and pillow-shaped structures. Over time, as the eruption continues, these individual pillows pile up, creating thick layers of volcanic rock that form the upper part of the oceanic crust. Each pillow is a snapshot of a single pulse of lava, frozen in time. Studying these pillow lavas provides geologists with vital clues about the conditions of past eruptions. The glassy rind on the outside of each pillow cools so quickly that crystals do not have time to form, trapping a sample of the magma's original chemical composition. The shape and size of the pillows can indicate the speed and volume of the lava flow. By drilling deep into the oceanic crust, scientists can analyze layers upon layers of these ancient pillows, reading the history of the seafloor spreading process like the pages of a book. These humble, rounded rocks are silent storytellers of the deep. The volcanic activity at mid-ocean ridges does more than just create new rock. It also sustains one of the most bizarre and extraordinary ecosystems on our planet. In 1977, scientists exploring the Geolapis Rift, a section of the mid-ocean ridge in the Pacific, made a discovery that would forever change our understanding of life. They found bustling communities of strange creatures thriving in the complete darkness of the deep sea, clustered around vents spewing hot, mineral-rich water from the seafloor. These were hydrothermal vents, and they existed in a world powered not by sunlight but by chemical energy from the Earth's interior, a process known as chemosynthesis. These vents are a direct consequence of the volcanism at the ridges. Cold seawater seeps down into the newly formed, fractured crust. As it gets closer to the magma chambers beneath the ridge, the water is heated to extreme temperatures, sometimes over 400 degrees Celsius. This superheated water becomes highly corrosive, dissolving minerals and chemicals from the surrounding volcanic rock. It then rises buoyantly and erupts back into the ocean from fissures on the seafloor. When this hot, mineral-laden fluid mixes with the cold, oxygen-rich seawater, the dissolved minerals precipitate out, forming towering, chimney-like structures that can be black, white, or grey. These vents, often called black smokers or white smokers, are essentially chemical oases in the vast desert of the deep ocean. The water they release is rich in compounds like hydrogen sulfide, which are toxic to most life forms we know. However, for a specialized group of bacteria and archaea, this chemical soup is a source of energy. Through chemosynthesis, these microbes use the chemical energy from hydrogen sulfide to create organic matter, in much the same way plants on the surface use sunlight for photosynthesis. These remarkable microbes form the very base of the entire hydrothermal vent food chain, supporting a vibrant and unique ecosystem. Around these vents, life flourishes in astonishing abundance. Giant tube worms, some over 2 meters long, have no mouth or gut but house chemosynthetic bacteria within their bodies, which provide them with all the nutrients they need. Dense colonies of giant clams and mussels filter the water, while ghostly white crabs and shrimp scuttle across the seafloor, grazing on bacterial mats. This entire world, with its strange and wonderful inhabitants, is completely dependent on the heat and chemicals supplied by the underwater volcanoes of the mid-ocean ridge. It is a powerful reminder that life can find a way in the most extreme environments imaginable. The Mid-Ocean Ridge System is a planetary-scale construction project that has been operating for hundreds of millions of years. Its primary function is the creation of new oceanic crust, a process that effectively resurfaces more than two-thirds of our planet over geological time. This renewal is not just a surface-level phenomenon, it is a fundamental part of the Earth's life cycle, intricately linked to the chemistry of our oceans and atmosphere. As new crust is formed at the ridges, it moves slowly outwards like a pair of giant conveyor belts carrying the seafloor away from its volcanic birthplace. This journey can take up to 200 million years. As the crust travels, it ages. It cools, contracts, and becomes denser, causing it to sink deeper into the mantle and form the vast, flat abyssal plains. During its long journey across the ocean basin, the volcanic rock interacts extensively with the seawater. This process, known as hydrothermal alteration, changes the chemical composition of both the crust and the ocean. Elements are exchanged between rock and water on a massive scale. This slow, continuous chemical reaction plays a crucial role in regulating the long-term composition of the world's oceans, influencing factors like salinity and the concentration of essential nutrients that support marine life far from the ridges themselves. Ultimately, the journey of the oceanic crust comes to an end. When it collides with a continental plate or a younger, more buoyant oceanic plate, its high density causes it to bend and sink back into the mantle in a process called subduction. These subduction zones, often marked by deep ocean trenches, are the recycling plants of plate tectonics. As the old, cold and chemically altered crust descends, it carries water and sediments with it deep into the Earth's interior. This process fuels a different kind of volcanism, the explosive volcanoes that form volcanic arcs on the overriding plate like the ring of fire around the Pacific Ocean. This grand cycle from creation at mid-ocean ridges to destruction at subduction zones is the engine that drives our planet. It is a slow but relentless process of resurfacing. The silent, ceaseless volcanism of the mid-ocean ridge builds the seafloor, which then acts as a giant chemical reactor for millions of years before being recycled. This system dictates the shape of the continents, the chemistry of the oceans, and the location of earthquakes and volcanoes on land. It is the planet breathing, a cycle of birth, life, and renewal on a scale that is almost impossible to imagine, all orchestrated from the secret volcanic depths. Beyond the sprawling, continuous mountain chain of the mid-ocean ridge, the seafloor is, dotted with thousands of individual volcanic mountains. These are the seamounts, colossal structures that rise from the abyssal plains like silent, solitary sentinels. A seamount is formally defined as any isolated peak rising at least 1,000 meters from the surrounding seafloor. There are estimated to be over 100,000 of these mountains scattered throughout the world's oceans, with, honestly, many more smaller volcanic hills. Most never reach the sunlit surface waters, their entire existence playing out in the cold, dark, high-pressure world of the deep. They are true mountains in every sense. Some towering higher than any peak on land if measured from their base on the ocean floor. These underwater volcanoes are fundamentally different from those found at the mid-ocean ridges. While ridge volcanoes are born from the pulling apart of tectonic plates, most seamounts form far from these plate boundaries, in the middle of the vast oceanic plates. They are the result of localized sources of intense heat deep within the Earth's mantle, known as hotspots. A plume of unusually hot rock rises from the deep mantle and punches its way through the overlying tectonic plate, kind of like a blowtorch burning through a sheet of steel. This creates a volcano on the seafloor that can grow over millions of years, eruption by eruption, building a massive cone on the otherwise flat abyssal plain. The sheer number and scale of these seamounts are frankly breathtaking. The Pacific Ocean, in particular, is studded with them. Many form long, linear chains tracing the path of a tectonic plate over a stationary hotspot. Others appear in clusters or as completely isolated peaks. For centuries, their existence was unknown to us, a hidden topography concealed by the waves. Sailors might have occasionally noticed strange currents or unusually shallow waters in the open ocean, but the true nature of what lay beneath remained a mystery. It's only with the advent of modern sonar mapping that we have begun to appreciate the true geography of this submerged world and the sheer abundance of these hidden mountains. Each seamount is its own self-contained world. Its rugged slopes and volcanic summit provide a hard surface in an environment that is otherwise dominated by soft mud and sediment. This solid foundation becomes a critical anchor for life, a place where corals, sponges, and other filter-feeding organisms can attach and grow. The very presence of the mountain disrupts deep ocean currents, creating complex flow patterns that stir up nutrients from the depths. These silent, dark mountains, born of fire in the abyss, are not just geological features. They are pivotal to the distribution of life in the deep ocean, creating islands of biodiversity in the vast expanse of the seafloor. To understand how these great seamount chains and volcanic islands are born, we must journey deep into the earth, far below the crust. The engine for their creation lies in the mantle, the thick layer of hot, solid rock that makes up the bulk of our planet's interior. While the mantle is mostly solid, it churns and convects over geological timescales, like a very thick, slowly boiling pot of soup. In certain places, narrow plumes of exceptionally hot rock are thought to rise from the deepest parts of the mantle, perhaps even from the boundary with the Earth's core. These are mantle plumes, the driving force behind hotspot volcanism. They are relatively stationary, fixed points of intense heat deep within the planet. As a tectonic plate, which forms the rigid outer layer of the Earth, drifts slowly over one of these fixed mantle plumes, the story begins. The intense heat from the plume acts like a powerful blowtorch, heating and melting the base of the plate. This generates large quantities of magma, which is less dense than the surrounding rock and begins to rise towards the surface. It pools in magma chambers within the crust before eventually erupting onto the seafloor. This marks the birth of a new submarine volcano, a new seamount directly above the hotspot. It is an echo of the mantle's deep heat made manifest on the ocean floor. Unlike the volcanism at mid-ocean ridges, which creates long, linear mountain ranges, hotspot volcanism is focused on a single point. This allows for the construction of enormous individual volcanoes. Over millions of years, countless eruptions build the volcano higher and higher, layer upon layer of lava. The volcano grows from the sea floor, a massive shield-like structure taking shape in the darkness. As long as this part of the tectonic plate remains over the hot spot, the volcano will remain active, fed by a constant supply of magma from the mantle plume below. It is a period of vigorous growth, a mountain being built from the inside out. However, the tectonic plates are perpetually in motion. The Pacific Plate, for instance, is sliding towards the northwest at a rate of several centimeters per year. As the plate moves, it carries the newly formed volcano with it, away from the stationary mantle plume. Cut off from its source of magma, the volcano's fires die out. It becomes dormant and then extinct. Meanwhile, the section of the plate that is now positioned over the hotspot begins to feel the heat. A new volcanic center is established, and the process of building a new seamount begins all over again. This creates a distinct age-progressive chain of volcanoes on the seafloor. There is no better place on Earth to witness the magnificent power of hotspot volcanism than the Hawaiian Islands. This iconic archipelago is the world's most famous and well-studied example of a hotspot track. The islands we see today, Oahu, Maui, and the Big Island of Hawaii, are merely the youngest, and in some cases still active members of a much longer chain of volcanoes that stretches for nearly 6,000 kilometers across the Pacific seafloor. This entire chain was created by the Pacific Plate moving steadily over a single persistent mantle plume that has been active for at least 80 million years. It is a geological conveyor belt of creation. The process is laid out with beautiful clarity. The Big Island of Hawaii, sitting directly atop the hotspot today, is the youngest and most volcanically active island. It is home to Kilauea, one of the most active volcanoes on the planet. As we travel northwest along the island chain, the islands become progressively older, more eroded and less volcanically active. Maui, Oahu and Kauai are the remnants of older volcanoes that have long since been carried away from the hotspot. Their deep, eroded valleys and weathered peaks tell a story of great age. They are the sleeping ancestors of the active volcanoes we see on the Big Island. If we follow this chain further to the northwest, beyond the main Hawaiian islands, the volcanoes disappear beneath the waves. Here they continue as a long line of submerged, extinct volcanoes known as the Hawaiian seamounts. These are former islands that have slowly sunk back into the ocean. Over millions of years, the cooling oceanic crust beneath them becomes denser and subsides. At the same time, the forces of erosion, wind, rain and waves, relentlessly wear the volcanic peaks down. Eventually, the island sinks below the surface, becoming a seamount once more. Many are now flat-topped, their peaks having been planed off by wave action when they were at sea level. This remarkable chain does not end there. About 2/3 of the way along its length, it takes a sharp bend and continues northward. This section is known as the Emperor Seamount Chain. This bend, dated to around 47 million years ago, records a dramatic change in the direction of the Pacific Plate's motion. The entire Hawaiian Emperor Seamount Chain is therefore a spectacular physical record of the movement of a tectonic plate over a fixed point in the Earth's mantle. It is a dotted line drawn across the seafloor by a volcanic pen, telling a story of continental drift, eruptive power and the slow, inevitable return of mountains to the sea. The birth of a volcanic island is honestly one of the most dramatic events in geology. It's the culmination of a process that begins in darkness, thousands of meters below the ocean's surface. It all starts with the formation of a seamount over a hotspot. For millions of years, the volcano grows, eruption after eruption, building its cone higher and higher from the abyssal plain. Its slopes are paved with bulbous pillow lavas, which are really the hallmark of deep submarine eruptions. As it grows, it passes through different ocean layers, each with its own pressures and conditions. It's a mountain ascending through a liquid sky, destined for the world of air and light. As the summit of the growing volcano approaches the sea surface, the nature of its eruptions changes dramatically. The confining pressure of the water decreases, allowing the volcanic gases within the magma to expand with explosive force. The interaction between superheated magma and seawater becomes violent, producing powerful steam explosions known as phreatomagmatic eruptions. These blasts shatter the magma into tiny fragments of ash and rock, building up a cone of loose material around the vent. This is, without a doubt, the most volatile and dangerous stage of the volcano's life, as witnessed during the Surtsey eruption off the coast of Iceland in 1963, which built a new island from the seafloor in just a few years. If the eruption has enough power and persistence, the volcanic cone will eventually break the surface of the ocean. A new island is born. Once the vent is established above sea level, the calming influence of the water is gone. The eruptions can become more effusive, producing spectacular lava fountains and flowing rivers of molten rock that pour into the sea, creating new land. The island grows, its coastline expanding with each new flow. At this stage, the forces of creation have triumphed over the forces of the ocean. The island becomes a new, solid piece of territory, ready to be colonized by life. But from the moment it is born, an island is also destined to die. Once it is carried away from the hotspot by the moving tectonic plate, its volcanic heart grows cold. The eruptions cease and the forces of erosion begin their relentless work. Rain, wind, and pounding waves start to wear the island down, carving valleys and cliffs into its volcanic slopes. At the same time, the oceanic crust beneath the immense weight of the island slowly cools and subsides, causing the island to sink. Over millions of years, the once mighty volcanic peak is worn down to sea level and then sinks beneath the waves, becoming a flat-topped seamount or guyot, its journey complete. Seamounts are far more than just geological curiosities. They're vibrant hubs of life in the deep ocean. Biological oases that stand in stark contrast to the sparsely populated abyssal plains surrounding them. The very structure of these underwater mountains is what makes them so attractive to marine organisms. Their steep rocky slopes provide a vital hard substrate in a world otherwise dominated by soft, deep-sea mud. This solid footing allows a huge variety of sessile or fixed animals to gain a foothold. Ancient, slow-growing deep-sea corals, colourful sponges and delicate sea fans can attach to the rock, forming dense gardens and forests that can be hundreds or even thousands of years old. These coral gardens and sponge fields create complex three-dimensional habitats that in turn provide shelter and food for a host of other creatures. Brittle stars wrap their arms around coral branches, while crabs and lobsters hide in the crevices between the rocks. These rich invertebrate communities form the foundation of a complex food web. The presence of a seamount also has a profound effect on the surrounding water. As deep ocean currents, which flow like slow-motion rivers, encounter the massive obstacle of a seamount, they are forced upwards. This process, known as upwelling, carries nutrient-rich water from the depths towards the sunlit surface layers. This injection of nutrients into the upper ocean fuels blooms of phytoplankton, the microscopic plants that form the base of the marine food web. These blooms attract zooplankton, which in turn attracts small fish, squid, and other predators. This creates a highly productive ecosystem that draws in larger migratory species from across the ocean. Tuna, sharks, billfish, and marine mammals like whales and dolphins are all known to congregate over seamounts to feed. For this reason, seamounts are often referred to as biological hotspots, acting as crucial stepping stones, feeding stations, and navigational landmarks for a vast array of marine life. Because of their isolation, many seamounts are also home to a high number of endemic species, creatures found nowhere else on Earth. Each seamount can be like an isolated island, leading to the evolution of unique life forms. Scientists exploring these hidden worlds are constantly discovering new species, from bizarre fish to previously unknown corals. However, these fragile, ancient ecosystems are extremely vulnerable to disturbance. Destructive fishing practices like bottom trawling can destroy millennia-old coral gardens in a single pass, while the prospect of deep-sea mining for minerals on seamount crusts poses a significant threat to habitats we are only just beginning to understand. Seamounts are more than biodiversity hotspots. They're time capsules of Earth's history. Their volcanic chains, like the Hawaiian Emperor chain, reveal the movement of tectonic plates over millions of years. Sediment layers and iron-manganese crusts on seamounts record past ocean conditions and climate cycles, offering clues to ancient environments. These crusts also concentrate valuable metals, making seamounts targets for deep-sea mining, a challenge for conservation. Seamounts teach us about evolution, resilience, and the health of our oceans, acting as refugees and sources for marine life. They are guardians of our planet's past and signposts to its future, reminding us how much remains to be explored. Underwater volcanoes are tamed by the immense pressure of the ocean above them. This hydrostatic lid suppresses explosive eruptions, forcing magma to ooze quietly as pillow basalts along the seafloor. At great depths, volcanic gases stay dissolved, preventing violent blasts common on land. Most of Earth's volcanic activity is this silent, steady process, building new crust in the deep. Yet these eruptions release vast heat and chemicals, fueling hydrothermal vents and unique ecosystems. The true power of deep-sea eruptions lies in their cumulative impact on ocean chemistry and temperature. The ocean's weight transforms volcanic fury into a slow, relentless force shaping our planet. The ocean is the ultimate testbed for effusive versus explosive eruptions. Deep below, high pressure keeps eruptions gentle. Lava flows quietly, forming pillow lavas. Explosive eruptions require gas expansion, which is suppressed at depth. The critical depth for explosive activity is around 500–1,000 meters. Below this, eruptions remain effusive. Above this depth, lower pressure allows gases to expand, and magma-water interactions can trigger violent blasts. In shallow waters, phreatomagmatic eruptions occur as magma vaporizes seawater, unleashing explosive energy. The ocean's depth determines whether a volcano whispers or roars. As submarine volcanoes rise into shallower waters, the pressure lid weakens, unleashing explosive potential. Here, expanding volcanic gases and violent magma-water interactions combine for phreatomagmatic eruptions. These eruptions can blast ash, steam, and volcanic bombs skyward, as seen at Surtsey in 1963. The energy can trigger shockwaves, tsunamis, and rapidly build new islands. Shallow water eruptions threaten shipping, aviation, and coastal populations with ash clouds, pyroclastic flows, and tsunamis. The world's busiest coasts often lie near these hidden hazards. The shallow water zone is where submarine volcanoes become truly dangerous. In January 2022, Tonga Ha'apai erupted with unprecedented force, demonstrating the peril of shallow water volcanoes. The blast was heard thousands of kilometers away and sent pressure waves around the globe. Its eruption column soared 58 kilometers into the mesosphere, the highest ever recorded. The explosion generated tsunamis that devastated Tonga and reached distant shores. Over 140 million tons of water vapor were injected into the stratosphere, with potential climate impacts still being studied. This event was a stark reminder of the global reach of submarine eruptions. The ocean's hidden volcanoes can shake the world. Submarine volcanoes pose diverse, often hidden threats, from explosive blasts to massive landslides and tsunamis. Flank collapses can trigger megatsunamis, as seen in Hawaii and the Canary Islands. Eruptions release toxic gases and deoxygenated water, devastating marine life and altering ocean chemistry. Most seamounts remain unmapped and unmonitored, leaving us blind to many risks. Advances in technology help, but the ocean's scale keeps many hazards hidden. The silent power of underwater eruptions shapes our world in ways we're only beginning to understand. Beneath the waves, Earth's greatest forces remain out of sight until they make themselves known. The most terrifying and immediate hazard posed by submarine volcanoes is their ability to generate tsunamis. These are not the wind-driven waves we see breaking on the shore every day. They are immense, powerful pulses of energy that travel through the entire water column from the seafloor to the surface. A submarine eruption can displace a colossal volume of water in just a matter of seconds, creating a disturbance that can propagate across an entire ocean basin. The sudden upward thrust from an underwater explosion acts like a giant piston, lifting the sea surface above it. Gravity then pulls this dome of water back down, creating a series of waves that race outwards in all directions at, incredible speeds. In the deep ocean, a tsunami wave may be barely noticeable, maybe only a meter high, with a wavelength stretching for hundreds of kilometers. A ship in the open sea might pass over one without its crew even realizing the immense energy moving beneath them. The true danger of a tsunami is only revealed when it reaches the shallow waters of a coastline. As the sea floor rises, the energy of the wave is compressed into a smaller volume of water. The wave slows down dramatically, but its height increases catastrophically. This is how a subtle swell in the deep ocean can transform into a towering wall of water, 10, 20, or even 30 meters high, capable of inundating coastal communities with irresistible force. The 2022 eruption of Tonga Ha'apai provided a vivid modern example of this terrifying process. The cataclysmic explosion, which occurred just 150 meters below the surface, violently displaced the surrounding water, generating a tsunami that caused widespread devastation in the nearby nation of Tonga. But its reach was global. The wave traveled across the entire Pacific Ocean, a basin that covers 1/3 of our planet's surface. It caused significant damage and tragic fatalities in Peru, more than 10,000 kilometers away. It was a stark reminder that the consequences of a single submarine eruption are not confined by geography. They can connect continents in a shared moment of peril. This direct displacement of water by an explosive blast is just one of the ways a submarine volcano can unleash the ocean's fury. The eruption can also trigger other events that are equally, if not more effective at generating tsunamis. The rapid release of hot gas and ash can create pyroclastic flows that race across the sea surface, pushing water ahead of them. The collapse of the erupting caldera, the vast crater left behind by the explosion, can cause the seafloor to suddenly drop, pulling the overlying water down with it and initiating a wave. These complex, interconnected processes make predicting the size and impact of a volcanic tsunami an immense scientific challenge. While explosive eruptions are a potent source of tsunamis, an even greater threat may lurk in the silent, immense slopes of the volcanoes themselves. Submarine volcanoes are not solid, stable structures. They are vast, loose piles of fragmented rock, lava flows, and volcanic ash built up layer by layer over millennia. Their flanks are often incredibly steep and gravitationally unstable, like a precarious pile of sand waiting for the slightest nudge to collapse. An eruption, an earthquake, or even just the relentless pull of gravity over time can be enough to trigger a catastrophic failure, sending a vast section of the volcano sliding into the abyss. This is a submarine landslide, and it is one of the most efficient ways to generate a truly gigantic tsunami. Imagine a piece of a mountain, many cubic kilometers in volume, suddenly breaking free and sliding down the underwater slope at high speed. This immense mass of moving rock and debris acts like a giant paddle, displacing a phenomenal amount of water with incredible force. The scale of these events can dwarf even the largest explosive eruptions. The energy transferred to the water is immense, creating a wave that can be far larger and more destructive than one generated by a volcanic blast alone. The initial wave height near the source of the landslide can be hundreds of meters, a true megatsunami that would be almost unimaginable to a witness on a nearby shore. The Hawaiian Islands, which are the visible peaks of the world's largest volcanoes, provide sobering evidence of this hazard. The seafloor around the islands is littered with the debris from colossal ancient landslides. The Nuuanu landslide, which broke off the northeastern side of Oahu around 1.5 million years ago, was one of the largest on Earth. A section of the island the size of a modern city collapsed into the sea, sending debris scattering for over 200 kilometers across the ocean floor. The tsunami generated by such an event would have been apocalyptic, likely inundating the other Hawaiian islands with waves reaching heights of several hundred meters. This is not a theoretical risk, it is a recurring part of the life cycle of these volcanic giants. The threat is not confined to the Pacific. In the Atlantic, the Cumbre Vieja volcano on La Palma in the Canary Islands has been identified as a potential source of a future flank collapse. While the immediate likelihood of such an event is debated among scientists, the potential consequences are stark. A large-scale collapse there could generate a tsunami that would not only devastate the nearby coasts of Africa and Europe, but would also travel across the entire Atlantic Ocean, potentially causing significant damage to the east coast of the Americas. The silent, sleeping flanks of these volcanic mountains represent a hidden, low-probability but extraordinarily high-impact hazard to the entire world. Our understanding of the terrifying potential of volcanic tsunamis does not come solely from modern events or computer models. It is written in the geological record etched into the coastlines and landscapes of our planet. Geologists act as detectives, searching for the telltale signs left behind by gigantic waves that struck long before human history was recorded. These clues can be subtle, but they tell a story of oceanic power that far exceeds anything witnessed in modern times. By studying these ancient deposits, we can reconstruct the history of megatsunamis and gain a humbling perspective on the forces that have shaped our world and could one day be unleashed again. One of the most compelling pieces of evidence is the presence of chaotic deposits of marine material found far inland and high above the current sea level. Imagine finding deep-sea shells, coral fragments and beach sand mixed together in a jumbled layer on a hillside, hundreds of meters above the shore. Such a deposit cannot be explained by normal sea level changes. It can only have been put there by an immense wave that picked up material from the ocean floor and hurled it onto the land. By dating these deposits, scientists can pinpoint when these giant tsunamis occurred and begin to link them to specific catastrophic events, like the collapse of a nearby submarine volcano. The Hawaiian Islands are again a key location for this research. On islands like Lanai and Molokai, geologists have discovered marine deposits more than 300 meters above sea level. These deposits contain coral fragments that could only have come from the reefs far below. The evidence strongly suggests that these islands were struck by waves of almost inconceivable height, generated by the great submarine landslides from neighboring volcanoes like Oahu and the Big Island. These ancient scars on the landscape serve as a permanent warning, a physical record of the immense destructive power that these volcanic systems are capable of unleashing. This evidence is not limited to Hawaii. Around the world, from the Mediterranean to the coasts of Norway, scientists have found similar evidence of giant waves triggered by submarine landslides. The Storegga slide, which occurred off the coast of Norway about 8,000 years ago, was a landslide so large that it generated a tsunami that left deposits across Scotland, England, and the Faroe Islands. While this particular slide was not volcanic, it demonstrates the principle on a massive scale. By reading these geological scars, we learn that megatsunamis are a natural, albeit rare, part of Earth's system, driven by the inherent instability of the vast hidden topography beneath the ocean's surface. Beyond the immediate kinetic violence of tsunamis and landslides, submarine volcanoes pose another, more insidious hazard. They are a major source of gases and chemical compounds that are injected directly into the deep ocean, altering the water chemistry in ways that can be profoundly damaging to marine life. When a volcano erupts, it releases not only lava but also vast quantities of dissolved gases from the Earth's mantle, including carbon dioxide, sulfur dioxide, hydrogen sulfide, and methane. While deep-sea pressure may suppress explosive activity, it cannot stop this chemical release. The volcano effectively breathes these compounds into the surrounding water with potentially lethal consequences. A large submarine eruption can create what is known as a mega plume, a vast rotating lens of warm, chemically altered water that can spread out over thousands of square kilometers. The water is often highly acidic as gases like carbon dioxide and sulfur dioxide dissolve to form carbonic and sulfuric acid. It is also severely depleted in oxygen, a condition known as hypoxia or anoxia. For most marine animals, from fish to crustaceans, entering such a plume is a death sentence. The combination of low oxygen and corrosive acidity can cause mass die-offs, creating a dead zone that can persist for months or even years after the eruption itself has ended. This chemical hazard is not just a localized phenomenon. The release of vast quantities of carbon dioxide, a potent greenhouse gas, can have wider implications. While much of it is absorbed by the ocean, contributing to long-term ocean acidification, some can eventually find its way into the atmosphere. Methane, another powerful greenhouse gas, is often stored in a frozen ice-like state called methane hydrate in the sediments around submarine volcanoes. A sudden increase in heat from an eruption could destabilize these deposits, causing a massive abrupt release of methane gas into the ocean and atmosphere, an event that has been linked to rapid climate change events in Earth's deep past. Furthermore, the release of toxic elements like mercury, arsenic, and lead can contaminate the local ecosystem. These toxins can be absorbed by microscopic organisms at the base of the food web and then become progressively more concentrated as they move up to larger predators, a process called biomagnification. This can lead to high levels of toxicity in commercially important fish species, posing a potential risk to human health. The silent chemical outgassing of submarine volcanoes is a hidden hazard, a slow-acting poison that can disrupt marine ecosystems and impact the delicate chemical balance of our oceans on a grand scale. Given the immense destructive potential of tsunamis and other submarine hazards, the ability to monitor underwater volcanoes and provide early warnings is of critical importance to coastal communities around the world. However, this is, honestly, one of the greatest scientific and logistical challenges we face. The sheer vastness and hostility of the deep ocean environment make continuous surveillance incredibly difficult. Unlike land volcanoes, which we can observe with satellites, GPS, and ground-based sensors, submarine volcanoes operate in a realm of darkness and crushing pressure hidden from our direct view. So we are often forced to search for subtle, indirect clues that a hidden giant may be stirring. Our first line of defense is often remote sensing from afar. A global network of seismometers can detect the faint tremors known as harmonic tremor that are often associated with magma moving beneath a volcano. Hydrophones, which are essentially underwater microphones, can be deployed to listen for the sounds of submarine eruptions or landslides. Satellite altimetry, which measures the height of the sea surface with millimeter precision, can sometimes detect the slight bulge in the ocean caused by a rising body of magma beneath the sea floor, or, more critically, the initial formation of a tsunami wave in the open ocean after an event has occurred. For more direct monitoring, the DART, or Deep Ocean Assessment and Reporting of Tsunamis system, is a crucial tool. This network consists of buoys stationed at strategic locations throughout the world's oceans. Each buoy is linked to a pressure sensor on the seafloor. This sensor can detect the tiny change in pressure caused by a passing tsunami wave. When it detects a signal, it relays the information to the surface buoy. which then transmits it via satellite to tsunami warning centers in real time. This system does not predict the eruption or landslide itself, but it provides vital confirmation that a tsunami has been generated, allowing for more accurate warnings to be issued to threatened coastlines. Ultimately, the future of monitoring lies in getting closer to the source. The use of robotic vehicles, such as autonomous underwater vehicles or AUVs, is revolutionizing our ability to survey these hazardous environments. These untethered submarines can be programmed to patrol the flanks of active submarine volcanoes, creating high-resolution maps, sampling water chemistry for signs of volcanic gas, and measuring temperature changes. The goal is to establish permanent cabled observatories on the seafloor at the most dangerous volcanoes, providing a continuous stream of data. It's a technological race against time, a constant effort to improve our eyes and ears in the deep, in the hope that we can better understand these powerful forces and mitigate their devastating impact. For most of human history, it was an undisputed fact that all life on Earth ultimately depended on the sun. Plants and algae on land and in the sea capture solar energy through photosynthesis, forming the base of nearly every food web on the planet. It was believed that, in the eternal darkness of the deep ocean, far below the reach of the sun's rays, life would be scarce, slow, and meager, subsisting only on the sparse rain of organic detritus falling from the sunlit world above. This fundamental assumption was shattered in 1977 by a discovery that would totally revolutionize our understanding of biology and the potential for life to exist in the most extreme environments. It was a discovery made in the volcanic heart of the mid-ocean ridge. A team of geologists diving in the small research submersible Alvin were exploring the Geolapis Rift, a section of the mid-ocean ridge in the eastern Pacific. They were searching for predicted hot springs, places where seawater heated by volcanic activity should be venting from the sea floor. What they found was far more extraordinary than they could have ever imagined. Instead of a barren, rocky landscape, they stumbled upon a scene of astonishing vitality. Clustered around fissures in the seafloor that shimmered with heated water were dense, bustling communities of bizarre creatures. It was a vibrant, thriving ecosystem, an oasis of life existing in total darkness and under immense pressure, seemingly in defiance of all known biological rules. The scene that greeted the astonished scientists was like something from another world. Towering lipstick-red tube worms, some over 2 meters in length, swayed gently in the currents, their white chitinous tubes anchored to the black volcanic rock. Dense beds of giant white clams and mussels, far larger than their shallow water relatives, carpeted the seafloor. Ghostly white crabs scuttled between the vents, and strange dandelion-like animals were tethered to the rocks. This was not a sparse community surviving on scraps from above. This was a rich, complex, and highly productive ecosystem teeming with life. The density of living matter around these vents was comparable to that of a lush rainforest or a vibrant coral reef. The most profound question was, what was powering this incredible abundance of life? With no sunlight available for photosynthesis, the energy had to be coming from somewhere else. The answer lay in the water gushing from the vents themselves. It was rich in chemicals, particularly hydrogen sulfide, a compound toxic to most known life forms. The scientists soon realized they were witnessing an entirely new form of existence, one based not on light but on chemistry. The energy source was not the sun but the volcanic heat of the Earth itself. This process, termed chemosynthesis, had been theorized for microbes, but no one had imagined it could support such a large and complex animal community. Hydrothermal vents are a direct and spectacular consequence of the volcanism that occurs at mid-ocean ridges and other submarine volcanic sites. They are, in essence, the planet's plumbing system, driven by the intense heat of magma chambers that lie just a few kilometers beneath the sea floor. The process begins when cold, dense seawater at a temperature of only about 2 degrees Celsius seeps down into the ocean crust through cracks and fissures in the young, porous volcanic rock. As this water percolates deeper, it journeys toward the Earth's fiery interior, its chemistry beginning a radical transformation along the way. It is a journey into a natural, high-pressure chemical reactor. As the seawater approaches the magma chamber, it is heated to extreme temperatures, often exceeding 400 degrees Celsius. At this temperature and under the immense pressure of the deep ocean, the water does not boil but becomes a supercritical fluid, a strange state between a liquid and a gas. This superheated, highly energetic fluid is incredibly corrosive. It aggressively strips minerals and chemical compounds from the surrounding volcanic rock. It becomes enriched with dissolved substances like sulfur, iron, manganese, copper, zinc, and gases such as hydrogen sulfide and methane, while losing its magnesium and sulfates. The ordinary seawater is transformed into a hot, acidic, and metal-rich soup. Being much hotter and therefore far less dense than the surrounding cold seawater, this altered fluid begins to rise rapidly back towards the sea floor. It surges upwards through the rock, seeking an escape route. When it finally emerges from a fissure, it erupts into the near-freezing ocean as a focused, jet-like plume. The dramatic visual spectacle that gives these vents their names occurs at this moment of mixing. As the hot, mineral-laden vent fluid collides with the cold, oxygen-rich seawater, the dissolved minerals instantly precipitate out, forming a cloud of fine-grained, solid particles. This is what creates the characteristic smoke. If the plume is rich in iron and sulfur compounds, the resulting particles are black, creating the iconic black smokers. These vents often build towering, chimney-like structures of sulfide minerals that can grow to heights of several tens of meters. If the vent fluid is cooler and contains minerals like barium, calcium, and silicon, the precipitate is pale, forming white smokers. These structures are more than just geological curiosities. They are the chemical engines of the vent ecosystem. They continuously supply the energy and raw materials that a unique group of microorganisms need to build life from scratch in the complete absence of sunlight. The life forms that thrive around hydrothermal vents are among the most peculiar and resilient on our planet, perfectly adapted to an environment of extremes that would be instantly lethal to almost any other creature. The conditions are brutal, crushing pressures hundreds of times greater than at the surface, total darkness, and a precarious existence balanced between the freezing cold of the deep sea and the scalding, toxic water jetting from the vents. Yet it is precisely this chemical-rich, superheated water that provides the foundation for the entire ecosystem. The true masters of this world are not the large animals we see, but the microscopic bacteria and archaea that have harnessed the power of chemosynthesis. These remarkable microbes are the primary producers of the vent community. In a process analogous to photosynthesis, they use the chemical energy stored in compounds like hydrogen sulfide, which is abundant in the vent fluid, to convert carbon dioxide into organic matter. They are the plants of the deep, creating food from inorganic chemicals spewed from the Earth's interior. These microbes form thick, slimy mats on the rocks around the vents, providing a source of food for grazing animals like shrimp, limpets, and strange, furry-looking yeti crabs. They also live suspended in the water, forming a bacterial snow that is filtered out by other animals. Many of the most iconic vent animals have taken this relationship a step further, evolving a symbiotic partnership with these chemosynthetic bacteria. The giant tube worm, Riftia pachyptila, is a prime example. This incredible creature has no mouth, no stomach, and no gut. Instead, its body cavity is packed with a specialized organ called a trophosome, which is filled with trillions of bacteria. The worm's bright red plume acts like a gill, absorbing hydrogen sulfide, carbon dioxide and oxygen from the water and delivering them via its circulatory system to its bacterial partners. The bacteria in turn produce all the nutrition the worm needs to survive and grow to its giant size. This symbiotic strategy is repeated in other vent animals. The giant clams and mussels that form dense beds around the vents also house chemosynthetic bacteria within their gill tissues. They live a life of mutual benefit, providing their microbial tenants with a safe home and a steady supply of chemicals in exchange for a constant source of food. This allows for an astonishing biomass to accumulate in what should be a barren food desert. The entire complex food web, from the bacterial mats to the grazing shrimp and the predatory fish and octopuses that hunt them, is built upon this remarkable biological innovation, a testament to life's ability to adapt and thrive in the most unlikely of places. The discovery of hydrothermal vent ecosystems did more than just reveal a new way of life. It provided a compelling new hypothesis for one of the greatest scientific questions of all time. Where and how did life on Earth begin? For decades, the prevailing theory, championed by Charles Darwin, was that life originated in a warm little pond on the surface, a primordial soup of chemicals energized by lightning or ultraviolet radiation from the sun. However, this scenario has its problems. The early Earth's surface was a violent place, bombarded by asteroids and exposed to intense radiation which could have easily destroyed the fragile organic molecules necessary for life. The discovery of vents offered an alternative protected cradle for life's first spark. The hydrothermal vent hypothesis suggests that life may have originated in the dark, protected environment of the deep sea, within the chemical-rich labyrinth of these underwater hot springs. Vents provide all the necessary ingredients in one convenient location. They offer a sustained source of chemical energy in the form of compounds like hydrogen sulfide and methane, a powerful alternative to sunlight. They create strong chemical gradients with hot, acidic and reducing fluid from the vent mixing with cold, alkaline and oxidizing seawater. These gradients are a form of disequilibrium, a battery that early life could have harnessed to power its metabolism. Furthermore, the mineral structures of the vents themselves may have played a crucial role. Specifically, a cooler, less violent type of vent known as an alkaline hydrothermal vent is considered a particularly promising candidate. The chimney structures of these vents are highly porous, riddled with a network of tiny interconnected mineral compartments. Scientists have proposed that these microscopic pockets could have acted as natural test tubes or primitive cell walls. They could have concentrated the chemical building blocks of life, amino acids and nucleotides from the surrounding water, allowing them to react and link together to form the first complex polymers like proteins and RNA, the precursors to life itself. This deep-sea origin story has several compelling advantages. The deep ocean would have protected the fragile, nascent life from the harsh conditions on the planet's surface, shielding it from sterilizing UV radiation and devastating asteroid impacts. The constant flow of chemicals through the vent systems would have provided a reliable and continuous source of energy and raw materials. While the debate between a surface-based or deep-sea origin of life is far from over, the discovery of hydrothermal vents has provided a powerful and plausible alternative. It suggests that the very same volcanic forces that shape our planet's crust may have also provided the perfect crucible for its biology. Hydrothermal vents are not only biological and chemical wonders, they're also geological factories that concentrate valuable minerals on the seafloor. As the superheated, metal-rich fluid from a black smoker erupts and mixes with cold seawater, the dissolved minerals precipitate out, building up massive deposits on the seabed. Over thousands of years, these deposits can grow into large mounds, rich in metals that are crucial to our modern economy. These formations, known as seafloor massive sulfide deposits, are essentially high-grade ore bodies containing significant concentrations of copper, zinc, lead, silver, and gold. They are the black gold of the deep ocean. As land-based mineral resources become more difficult and expensive to mine, the allure of these rich, untapped deposits in the deep sea has grown significantly. Mining companies and nations are increasingly looking to the abyss as a new frontier for resource extraction. The technology to operate at these depths is advancing rapidly, with robotic cutting machines and powerful suction systems being developed to excavate and lift the ore to a surface vessel. Proponents of deep-sea mining argue that it could provide a secure supply of the metals needed for everything from smartphones and computers to green technologies like wind turbines and electric car batteries. However, the prospect of mining these unique environments is fraught with immense controversy and profound ecological risks. Hydrothermal vent ecosystems are oases of life, home to many strange and unique species, a large number of which are found nowhere else on Earth. These ecosystems are incredibly fragile and slow to recover from disturbance. The mining process itself would be devastating. Robotic excavators would obliterate the vent structures and the communities living on them. The excavation would also kick up vast plumes of sediment that could drift for kilometers, burying nearby habitats and clogging the gills and feeding apparatus of filter-feeding organisms far from the actual mine site. The risks extend beyond the physical destruction. The noise and light from mining operations could disrupt the behavior of deep-sea creatures that have evolved in a world of silence and darkness. The process could also release toxic metals trapped within the sulfides into the water column, with unknown consequences for the wider marine food web. We are faced with a classic dilemma: the conflict between human economic needs and the preservation of a unique and poorly understood natural world. Many scientists and conservationists are calling for a moratorium on deep-sea mining until we have a much better understanding of these ecosystems and the full extent of the potential damage, arguing that we should not risk destroying these cradles of life before we have even had a chance to fully explore their secrets. Volcanoes have long been recognized as powerful agents of climate change. The colossal eruptions of land-based volcanoes can inject vast quantities of sulfur dioxide into the stratosphere, forming a reflective haze that can cool the entire planet for several years. However, the climatic influence of their submarine counterparts is more subtle, complex, and operates over much longer timescales. Submarine volcanoes play a crucial ongoing role in the Earth's carbon cycle, the intricate global system that moves carbon between the atmosphere, oceans, land, and life. They act as a slow, steady leak, releasing carbon dioxide and other greenhouse gases from the Earth's mantle directly into the ocean, a process that helps to regulate the planet's long-term climate thermostat. The primary source of this volcanic carbon is the mid-ocean ridge system. Along this 65,000-kilometer-long volcanic chain, magma from the mantle rises to form new oceanic crust. This magma contains dissolved gases, with carbon dioxide being a significant component. As the magma erupts onto the deep sea floor, the immense pressure keeps most of this CO2 dissolved in the water rather than allowing it to escape into the atmosphere. This direct injection of carbon into the deep ocean makes submarine volcanoes a fundamental part of the ocean's carbon budget. While the annual amount is small compared to human emissions, over geological time it is a significant natural source that has helped shape the chemistry of our oceans and atmosphere for eons. This volcanic carbon does not simply stay in the deep sea. It becomes part of the ocean's complex circulatory system, the global conveyor belt of currents that slowly moves water around the planet. This process can take centuries, but eventually the carbon-rich deep water will upwell to the surface in other parts of the world. Once at the surface, some of this dissolved carbon dioxide can be released into the atmosphere, contributing to the planet's natural greenhouse effect. This volcanic contribution is a vital piece of the puzzle for climate scientists trying to understand Earth's natural climate variability and how it has fluctuated between ice ages and warm periods over millions of years. Beyond carbon dioxide, submarine volcanoes also release significant quantities of methane, another potent greenhouse gas. In the cold, high-pressure environment of the deep sea, methane can become trapped in a frozen, ice-like form known as methane hydrate. Vast reservoirs of these hydrates are thought to be stored in the sediments on and around submarine volcanic systems. A change in ocean temperature or a pulse of heat from volcanic activity could potentially destabilize these deposits, leading to a large, abrupt release of methane. Such events have been linked to periods of rapid global warming in Earth's distant past, highlighting another powerful, albeit unpredictable, link between submarine volcanism and the global climate system. While the steady, everyday volcanism of the mid-ocean ridges plays a long-term regulatory role, Earth's history has been punctuated by episodes of truly cataclysmic submarine volcanism. These events, known as the formation of large igneous provinces, involve the outpouring of immense volumes of lava over a relatively short geological timescale, often covering millions of square kilometers of the seafloor. These are not your typical volcanic eruptions. They are planetary-scale floods of basalt that have been directly linked to some of the most severe environmental crises and mass extinction events in our planet's history, primarily through their profound impact on the climate. A prime example is the Tonga Plateau in the western Pacific Ocean. Formed around 120 million years ago, it is the largest large igneous province on Earth. A vast underwater plateau of volcanic rock larger than the country of India. The eruption that created it was so enormous that it is believed to have released a catastrophic amount of carbon dioxide and other gases into the ocean and atmosphere. This massive injection of greenhouse gases would have triggered a period of intense global warming, leading to a major disruption of the ocean's chemistry. Evidence from the geological record points to an oceanic anoxic event at this time, where the oceans became largely depleted of oxygen, causing a mass extinction of marine life. These ancient events serve as a stark warning of the power of volcanism to drive climate to a tipping point. The formation of a large igneous province represents the Earth's volcanic system going into overdrive, releasing millions of years' worth of mantle carbon in the geological blink of an eye. The resulting super greenhouse effect would have acidified the oceans, raised global temperatures dramatically, and starved the seas of oxygen. The environmental cascade would have been devastating for life, both in the sea and on land. Scientists studied the rock and fossil records of these events as natural experiments, learning how the Earth system responds to massive, rapid carbon emissions. The scary part is that we do not fully understand what causes these colossal volcanic outbursts. They appear to be linked to the arrival of the massive head of a new mantle plume at the base of the Earth's crust. While no such event is occurring today, their existence in the past reminds us that the Earth's geological stability is not guaranteed. The echoes of these submarine climate catastrophes, preserved in the rock record, demonstrate that the connection between deep Earth processes and the surface environment can be both powerful and devastating. They show how submarine volcanoes have, at times, held the fate of the entire planet's climate in their hands. While carbon dioxide is the primary gas we associate with long-term climate change, the 2022 eruption of Tonga Ha'apai highlighted the powerful, short-term climatic role of another, often overlooked volcanic emission water. The cataclysmic blast was unique not just for its explosive power, but for what it injected into the upper atmosphere. Because the eruption occurred at a shallow depth, it blasted a colossal amount of seawater along with ash and gas directly into the stratosphere. This event delivered an estimated 146 million tons of water vapor to a layer of the atmosphere that is normally incredibly dry, increasing the stratosphere's total water content by a staggering 10 to 15%. This is highly significant because water vapor is a potent greenhouse gas. In the lower atmosphere or troposphere, water vapor is part of the normal weather cycle and has a short lifespan. However, once injected into the stratosphere, above the weather, it can persist for several years, trapping heat that would otherwise escape into space. The Tonga eruption was, in effect, a massive atmospheric experiment. It was the first time in recorded history that an event had delivered such a huge and sudden injection of water vapor to this altitude, and scientists immediately began working to predict its climatic consequences, a rare opportunity to study a direct atmospheric perturbation. Unlike large land-based eruptions such as Pinatubo in 1991, which injected vast amounts of cooling sulfur dioxide, the Tonga eruption was relatively sulfur-poor. This meant its warming effect from the water vapor would not be cancelled out by a cooling effect from sulfate aerosols. Climate models predicted that the extra water vapor would temporarily enhance the greenhouse effect, leading to a small but measurable increase in global surface temperatures over the next few years. This submarine volcanic eruption, for a short time, would actively work against the cooling effect typical of large volcanic events, and instead add a small amount of extra fuel to ongoing global warming. True to the predictions, the years following the eruption have seen record-breaking global temperatures. While the primary driver of this heat is long-term human-caused climate change, many scientists believe the anomalous warming spike from the Tonga event has played a contributing role, pushing an already warming world into uncharted territory. The event served as a powerful reminder that submarine volcanoes can influence climate in unexpected ways. It is not just about the slow release of CO2 over millennia or the catastrophic burps of ancient large igneous provinces. A single well-placed shallow submarine eruption can directly and immediately tweak the Earth's energy balance through the simple yet powerful medium of water. The relationship between volcanoes and climate is not just a one-way street where volcanoes influence the climate. Emerging research suggests that climate change can, in turn, influence the frequency and intensity of volcanic activity, including that of submarine volcanoes. This creates a complex feedback loop where changes in the surface environment can be transmitted down to the Earth's crust and mantle, affecting the deep geological processes that lead to eruptions. One of the most significant mechanisms for this feedback is the change in pressure on the Earth's crust caused by the melting of massive ice sheets or changes in sea level. During ice ages, vast, heavy continental ice sheets, kilometers thick, press down on the Earth's crust. This immense pressure can suppress volcanic activity by clamping down on magma chambers and making it harder for magma to ascend. As the climate warms and these ice sheets melt, that pressure is released. This process, known as glacial unloading, can decompress the mantle beneath, promoting melting and making it easier for magma to erupt. Evidence from places like Iceland, where the mid-Atlantic ridge is covered by glaciers, shows that volcanic activity increased significantly as the ice sheets retreated at the end of the last ice age, suggesting a direct link between climate warming and increased eruptions. This principle also applies to submarine volcanoes, particularly through changes in sea level. While it may seem minor compared to an ice sheet, a change in sea level of 100 meters, as has happened between ice ages and warm periods, alters the pressure on the seafloor. A fall in sea level reduces the confining pressure on submarine volcanoes, potentially making eruptions more likely or more explosive, especially for those in the shallow water danger zone. Conversely, a rise in sea level increases the pressure, which could suppress eruptions. This suggests that the rhythm of submarine volcanism, especially along the mid-ocean ridges, may be subtly modulated by the planet's long-term climate cycles. As our current climate continues to warm, these feedback mechanisms become a critical area of research. The rapid melting of the Greenland and Antarctic ice sheets is reducing pressure on the land and, through sea level rise, increasing pressure on the seafloor. While the effects are likely to play out over centuries and millennia rather than years, it highlights the profound interconnectedness of the Earth system. The climate is not just a passive recipient of volcanic inputs, it is an active participant in a planetary dialogue where changes in the atmosphere and oceans can reach down and stir the fiery heart of the planet itself, creating feedback loops we are only just beginning to comprehend. Our journey into the world of underwater volcanoes began in the familiar fiery mountains of land, but it has led us deep into a hidden realm that is far more vast and influential. We have discovered that the true heart of our planet's volcanic activity beats not in the air, but beneath the immense pressure of the oceans. These submarine volcanoes, from the globe-spanning mid-ocean ridge to the solitary seamounts rising from the abyss, are the silent architects of our world. They are the primary engine of plate tectonics, the force that builds the very ground beneath the seas, moves the continents and dictates the fundamental geography of our planet. They are not merely a geological footnote, they are the main text of Earth's ongoing story of creation. The sheer scale of their influence is almost beyond comprehension. Every year, these unseen volcanoes pour out cubic kilometers of lava, constantly repaving the ocean floor and ensuring that the crust beneath the waves is, in geological terms, perpetually young. This ceaseless activity does more than just build rock. It regulates the planet's internal heat and drives a grand cycle of chemical exchange between the mantle and the oceans. The silent eruptions in the deep are a fundamental part of Earth's life support system, a slow, steady process that has shaped the world we know over hundreds of millions of years, working tirelessly in the dark to build the foundations of our blue planet. This hidden engine is not just a force of construction, it is also a source of life. We journeyed to the hydrothermal vents, the extraordinary chemical oases clustered around submarine volcanic systems. Here, in the total absence of sunlight, we found bustling ecosystems thriving on the energy provided by the Earth itself. These bizarre and wonderful communities, powered by chemosynthesis, have revolutionized our understanding of biology and offered a compelling new hypothesis for the very origins of life. They suggest that the first spark of existence on our planet may have been nurtured in the protected, energy-rich crucible of an underwater volcano, sheltered from the harsh conditions of the early Earth's surface. From the quiet, effusive flows of the deep abyss to the explosive, cataclysmic blasts in shallow waters. The character of submarine volcanism is one of profound contrasts. We have seen how the immense weight of the ocean can tame a volcano's fury, and how a release from that pressure can unleash its full, terrifying power. These hidden giants are a constant reminder that our planet is a dynamic and restless entity. They are a direct connection to the molten heart of the Earth, a powerful force that operates on a scale that dwarfs human experience, yet whose influence touches every aspect of our world, from the chemistry of the sea to the air we breathe. Throughout our exploration, we have witnessed the profound duality of submarine volcanoes. They are both creators and destroyers, forces of immense generation and terrifying peril, weaving a complex tapestry of existence on our planet. On one hand, they are the ultimate builders. Over eons, they have constructed the entire ocean floor piece by piece. They raise colossal seamounts from the abyssal plains, mountains that become oases for deep-sea life, and in their most dramatic act of creation, they breach the ocean surface, forging new islands from fire and water, creating fresh land for life to colonize in the middle of the vast ocean. The Hawaiian archipelago stands as a spectacular monument to this creative power. Yet this creative force is matched by an equally formidable capacity for destruction. An eruption in the shallow water danger zone, like that of Tonga Ha'apai, can unleash an explosion of unimaginable violence, sending shockwaves around the globe and triggering tsunamis that can devastate coastlines thousands of kilometers away. The very mountains these volcanoes build are inherently unstable. The silent, ever-present threat of a catastrophic flank collapse looms over many volcanic islands, a geological time bomb that could generate mega-tsunamis far larger than anything witnessed in modern history. The evidence of these ancient cataclysms is scarred into the landscape, a permanent warning of the peril that lies dormant beneath the waves. This duality extends beyond the physical realm. The same hydrothermal vents that may have cradled the origin of life also spew chemicals that can create vast, toxic dead zones in the ocean. The seafloor massive sulfide deposits they create, rich in the metals our technological society craves, are also home to some of the most unique and fragile ecosystems on the planet. The desire to exploit these resources puts us in direct conflict with the need to preserve these extraordinary biological communities, many of which we have only just discovered. The story of submarine volcanoes is therefore also a story of the difficult choices we face as stewards of the planet. This tapestry of creation and destruction is not a contradiction, but rather the fundamental nature of a living, dynamic planet. Earth is not a static museum piece, it is a world in a constant state of flux, of birth, growth, and renewal. The forces that create new land are the same forces that can sweep it away. The heat that nurtures life in the deep can also power cataclysmic explosions. To understand submarine volcanoes is to accept this profound and often unsettling duality. It is to appreciate that the Earth is a place of restless, creative and sometimes violent energy, a world that is always remaking itself from the inside out. Despite everything we have learned, the world of submarine volcanoes remains one of the last and greatest frontiers of exploration on our own planet. We have better maps of Mars than we do of our own seafloor. The vast majority of the ocean's depths lie uncharted, and it is estimated that there are over 1 million seamounts, most of which have never been seen by human eyes, let alone studied. Each one is a potential new discovery, a unique ecosystem, a geological puzzle waiting to be solved. We stand at the shore of a vast submerged continent of ignorance, with the greatest discoveries about our own world still lying ahead of us, hidden in the deep. The challenges of exploring this realm remain formidable. The crushing pressure, the corrosive salt water, and the absolute darkness of the abyss push the limits of our engineering and ingenuity. Yet we are now entering a golden age of deep-sea exploration. A new generation of advanced technologies is finally allowing us to pull back the curtain on this mysterious world. High-resolution sonar mapping from research vessels is revealing the hidden topography of the seafloor in stunning detail. And our robotic emissaries, remotely operated vehicles and autonomous underwater vehicles, are taking us to places we could once only dream of visiting. These robotic explorers are our eyes, hands, and scientific laboratories in the deep. Equipped with powerful lights, high-definition cameras, and sophisticated sensors, they can give us a front-row seat to an erupting volcano, collect samples of rock and water from a hydrothermal vent, and discover species of life completely new to science. The integration of artificial intelligence is accelerating this process, allowing these vehicles to make autonomous decisions, identify features of interest, and analyze vast amounts of data in real time. Each mission into the deep brings back a torrent of new information, constantly reshaping our understanding of how our planet works. This journey of discovery is not just about satisfying curiosity, it is a mission of critical importance. By exploring these hidden volcanoes, we can better assess the risks of tsunamis and other geological hazards that threaten coastal populations. We can unlock the secrets of life's origins and discover novel biological compounds that could lead to new medicines. We can understand the long-term drivers of our planet's climate and the health of our oceans. The abyss holds the answers to some of the most fundamental questions about our world, and the key to unlocking them lies in our courage and commitment to continue this great voyage of discovery. As we conclude our journey, it is clear that what happens in the dark, silent depths of the ocean has a profound and direct impact on our lives at the surface. The influence of submarine volcanoes is woven into the fabric of our world. From the shape of the continents and the air we breathe to the stability of our climate and the biodiversity of our seas. They are not a remote, disconnected phenomenon, but an integral part of the Earth system that sustains us. Understanding them is not merely an academic exercise, it is essential for safeguarding our future on this restless planet. The climatic influence of these volcanoes in particular highlights this deep connection. They are a vital part of the planet's long-term carbon cycle. But as we have seen, they can also cause abrupt and dramatic shifts. The echoes of ancient, large, igneous provinces remind us that the Earth's climate has tipping points and that massive volcanic events can push the system into crisis. And the startling eruption of Tonga demonstrated that even a single modern submarine eruption can inject enough material into the atmosphere to temporarily alter the global energy balance, a powerful interaction between the deep ocean and the high sky. As our own species continues to alter the planet's climate, understanding these natural feedback loops becomes more critical than ever. The relationship between a warming climate, melting ice, rising sea levels, and volcanic activity is a frontier of science that carries immense implications for future generations. The Earth system is a web of intricate connections, and pulling on one thread can have unforeseen consequences elsewhere. The story of submarine volcanoes teaches us that the world is more interconnected than we ever imagined, linking the fate of our atmosphere to the forces stirring in the planet's molten core. The hidden world of underwater volcanoes is a realm of mystery, power, and astonishing beauty. It reminds us that we live on a planet that is creative, destructive, and perpetually alive. These silent giants of the deep hold the secrets of our planet's past and critical lessons for its future. As we develop the tools to explore their domain and listen to the stories they have to tell, we are not just learning about geology, we are learning about our own place in the grand, dynamic story of Earth. The journey into the abyss is, in the end, a journey of self-discovery for humanity itself.